Hello, my name is Sooncheol Hwang. My presentation topic is a GPU-accelerated modeling of scalar transport based on Boussinesq-type equations. This is the contents of today's presentation. Growth in both pollutant emissions to the ocean and the contaminant spill accidents by human activities are aggravating the marine ecosystem. Exacerbation of ocean weather conditions due to global warmings makes it even more unpredictable. The understanding of scalar transport mechanism in coastal engineering is important for various applications, including oil spills, contaminant spills, and algal blooms. Since the pollutant transport is dominated by ocean currents, ocean hydrodynamics and nearshore dynamics contribute to the prediction of pollutant transport. Numerical modeling is one of the common approaches to investigate the flow and the scalar transport within the ocean. An integrated model solving the nonlinear shallow water equations and the depth-averaged advection-diffusion equation may be a practical choice for predicting the shallow water flow and scalar transport. Despite its practicality, the nonlinear shallow water equations have limitations in considering the irregular wave characteristics due to its assumptions, so the Boussinesq equations are mainly used to investigate the nearshore dynamics, where both nonlinear and dispersive effects of waves are important. The Boussinesq equations are computationally very expensive and require high-performance computing systems such as parallel computation and GPU computation. Topography and Linet developed Celeris Advanced, which is an open-source wave solver software that uses GPU instead of CPU for the high-speed computation of the Boussinesq equation. In this study, scalar transport model coupling the Boussinesq equation with the advection-diffusion equation was developed based on the Celeris Advanced and validated through benchmark tests. Celeris Advanced solved the extended Boussinesq equations derived by Madison and Sorensen. And the equations are like this. In here, Rbx and Rby are the additional eddy viscosity term due to the wave breaking, defined as like this. And where the eddy viscosity nu is calculated by various eddy viscosity formulation. Among them, a simple eddy viscosity formulation for the estimation of the eddy viscosity derived from Kennedy et al. Is used, which can be expressed by here. And the delta B is the dimensionless mixing length coefficient, and B is the linear proportional factor varying from 0 to 1. And in here, the eta star can be calculated by this formulation. And in here, the T star is the transition time, and T0 is the time when breaking began, and eta I and eta F are the threshold value for the initiation and the cessation of the wave breaking. Scalar transport model solves an depth-integrated advection-diffusion equation for tracing scalar transport and dispersion, which reads as here. And also in here, the K is the diffusivity coefficient involving molecular diffusivity K0 and breaking wave eddy diffusivity KBR, which gives equals to the eddy viscosity by setting the Schmidt number to 1. Celeris Advanced uses a hybrid finite volume, finite difference scheme in solving the governing equations. Discretization based on the second order well-balanced positivity preserving center of in the scheme, hereafter KB07, enables advective terms to be solved with finite volume method. The numerical fluxes at the interfaces can be calculated by here. And the rest terms, including eddy viscosity terms, are discretized by the central finite difference method. Unlike mass, scalar concentration can be over-dissipated when using KP07. Thus, Liu proposed an anti-dissipation modification method to preserve the steady state of the scalar concentration by introducing a non-dimensional smooth function. The modified scheme is given by here, where the dimensionless anti-dissipation function, this, can be calculated by here. Also, this anti-dissipation function vary from 0 to the negative n to 1. Now I will explain the numerical validations. The first benchmark test is scalar advection in a one-dimensional uniform flow. Initial condition for scalar concentration was given by this exponential function, and flow velocity was assumed as 1 meter per sec. Gradient size was used as 1 centimeter, and time step was used as 0.01 second. Diffusion terms were not considered to confirm the numerical diffusion, and the figure 1 shows the comparison results, and this result shows that the computed scalar advection is very consistent with the analytical solution without any numerical diffusion. Next, model validation was extended to a two-dimensional flow problem. A frictionless water tank has a constant depth of 1 meter, and the flow condition over the model domain is defined by this rotating flow. Besides, the initial scalar distribution is given by this circular equation. Similarly, gradient size and time step was used as 0.01, which is same with the previous benchmark test. Physical dissipation was ignored to investigate the numerical diffusion as with the one-dimensional flow problem. The result shows that the negligible level of numerical diffusion was found near the this discontinuous point of scalar concentration, but the initial scalar distribution was well maintained. Now, the third and final benchmark tests were associated with the hydraulic experiments. Third one is die advection in the wake behind the submerged island. Lloyd and Stansby studied the development of the wake behind a submerged island according to different flow condition and conical island. The conical island, located at the 5 meter downstream of the inlet, has various model geometry options according to side slope angle theta. Among them, SP402 condition was applied to the coupled model, and the detailed informations are as follows. When the Manning's roughness coefficient was 0.01, the computed V velocity didn't match the phase of the observed V velocity because the depth average model cannot fully consider the three-dimensional flow characteristics in the wake of conical island. So, Manning's roughness coefficient was used as 0.02 to match the observed V velocity in the wake, and the results of the die advection were compared accordingly. As you can see, the figure 6 and figure 7 shows the flow field and die advection comparison, and the computed results are very consistent with the observed data. Final benchmark test is die advection due to a solitary wave run-up on a slope with a conical island. Lynette et al. Studied kinematic changes of the breaking solitary wave propagating over the three-dimensional shape installed in an irregular shallow water bathymetry and performed a die experiment to identify the advection and dispersion process visually. This experiment observed the transport of die released at a fixed point in the wave propagation process by generating a solitary wave with 0.39 meter of wave height in the channel described in figure 8. At 9 gauges, the water level was observed while the dye advection was observed in the entire channel. In this benchmark test, the wind mode limiter used for physical dissipation was compared with the wave breaking model, as physical dissipation occurred during the propagation of the solitary wave. At gauge 1, 2, 4, 5, there was no significant difference between two models since the wave didn't break. However, at gauge 3 and 6, the maximum wave height decreased by 8.3 and 9.8% respectively as the wave breaking model was used. Similarly, at gauge 7, 8, 9, the maximum wave height fell 12.3, 12.3, and 12.1% respectively. The RMSE at gauge 7 shows the biggest difference as 0.0028 meter when using the limiter scheme and 0.0017 meter when using the wave breaking model. And this is the result of dye advection. The figure on the left side shows the experiment result, and figure on the right side shows the simulation results by coupled model in this study. And the animation shows the dye advection as time traveled. This is the conclusion. In this study, a SCALAR transport model solving the extended Boussinesq equation and the advection-diffusion equation was developed, and the wave breaking model was additionally implemented to consider the physical dissipation due to the wave breaking. Quantitative comparison results with the two analytical solutions shows an exact coincidence in one-dimensional flow, but a negligible level of numerical diffusion in two-dimensional rotating flow. The performance of the newly implemented wave breaking model was quantitatively assessed through benchmark tests, and it was confirmed that the consideration of the wind mode limiter imitating physical dissipation was no longer necessary. The results from 4 benchmark tests validated the accuracy of the coupled model, and the coupled model is expected to be used for real-time prediction of marine pollution disaster with high accuracy and computation efficiency. This is the references, and thank you for watching the presentation.